How are you, my friends? This is lecture number 9 from Calculus 1 lectures, derivatives of algebraic functions. And the objectives of this lecture, we will look at the generalized power rule. We have seen already in lecture number 8, but we will see more examples. Then we will look at the differentiability and continuity. Also, differentiability and vertical tangent lines. Now, this is the formula for generalized power rule we have seen in lecture number 8. Simple example here. Let's find the derivative of 3 minus 5x all to the power 7. So directly we can say 7. We leave the same function inside, 3 minus 5x to the power n minus 1, which is 7 minus 1 times the derivative of the inside, which is the g here, g of x, 3 minus 5x. This is 0, the derivative is 0, and this one is minus 5 only. So the final answer in the derivative, minus 35, 3 minus 5x all to the power 6. Let's look at this nice example. Let's find the derivative of square root of 4 minus x squared. So we can use the generalized power rule also. Let's rewrite this function here, square root of 4 minus x squared, as 4 minus x squared all to the power half. So half now is the n. So we bring, to find the derivative, we bring the half down, 4 minus x squared, half minus 1, times the derivative of the inside, 4 minus x squared, the derivative. This is the derivative here. So it will be half, and this one is minus half, and the derivative of 4 minus x squared will be minus 2x. You multiply this with this, you cancel the 2, so there is minus x, and this power negative, we can bring it down, and we write the final answer for the derivative as minus x divided by square root of 4 minus x squared. Let's define differentiability of the function. A function is differentiable, so the derivative exists at the point a if and only if f prime of a is equal to the limit of f of a plus h minus f of a divided by h as h goes to 0 whenever the limit exists. So we should have a value there. F prime of a is equal to that number. If the limit exists, then we say the function is differentiable. All right. Now, vertical and horizontal tangent lines. If we have a curve, sometimes we can have vertical tangents or horizontal tangents, and we have already oblique tangents. The normal questions we have done oblique tangent like this, but these are special cases, vertical tangents and horizontal tangents. Now let's define the vertical. The curve has a vertical tangent line at the point A, f of A, provided that f is continuous, it should be continuous, at A, and the limit of f prime, the limit of f prime, the derivative, as x goes to A from the right or from the left, it should be plus infinity, both plus infinity, or both minus infinity. So they are equal, the limits are equal, but they are infinity, not number. So we can say the function, the curve, the graph has vertical tangent. Now horizontal tangents, we have seen horizontal tangents occur when the derivative is equal to 0. So this is the horizontal like this, horizontal tangents. We have seen many questions before. Now let's look at this nice question. Find all the points on the graph of this f of x, x to the power half, minus x to the power 3 over 2, where the tangent line is either horizontal or vertical. So first we have to find the derivative of this function. f prime will be half x to the power half minus 1 minus 3 over 2 x to the power 3 over 2 minus 1. Just simplify that. It will be 1 over 2 square root of x, because half minus 1 is minus half. And this 3 over 2 minus 1 is already half, so it becomes 3 square root of x over 2. So all this now is the derivative of the function. Now, horizontal tangent occurs when the derivative is equal to 0. So we put all this derivative here is equal to 0. So now we have an equation. Take this on this side, cross multiply. 1 will be 3x, so x will be 1/3. At 1/3, x equals 1/3, we have horizontal tangent. To find the exact point, take 1/3 and replace it in the function here. So f of 1/3, square root of 1/3 minus square root of 1/3 cubed, because this is square root of x cubed, remember, 3 over 2. So simplify that, take 1/3 out. So it will be 2 over 3 square root of 3, this one here. Take this one outside, common factor, 1 minus 1 over 3, and then rationalize. So it will be 2 square root of 3 over 9. You can simplify that by yourself. Check it, please. So the point where the horizontal tangent is 1/3 for the x, and for the y, it will be 2 square root of 3 over 9. If you graph this function, at this point, you have horizontal tangent. Now the vertical, this is the solution continues here. The vertical tangent occurs when f prime is undefined. So look at, this is the same derivative. You see that one here? See, you can simplify this derivative. 1 over 2 square root of x minus 3 square root of x over 2, make the LCD. So it will be here 1 minus 3x divided by 2 square root of x. This is f prime, remember. So when f prime is undefined, the derivative, there is no derivative, it is undefined. So the denominator is 0. So we can say 2 square root of x is equal to 0, square both sides, x will be 0. Now this is x. To find the y, replace x in the function. F of 0 will be also 0. So at this point, at the origin, 0, 0, this graph has a vertical tangent. Now, differentiability and continuity. Differentiability implies continuity. If the function is differentiable at a certain point, it is continuous. This way, it's okay. The other way, not always. If the function is continuous, it needs not to be differentiable. Maybe, maybe not. So we say the converse is not true. And I will show you 3 examples, number 4, number 5, and number 6, where we have the function is continuous, but not differentiable. Now let's look at example number 4. Determine all the points where the function f of x is equal to square root of x squared is not differentiable. Now we know the square root of x squared is the same as absolute value of x, which is v-shaped, and it is continuous everywhere because the domain is all real numbers. Now, one easy way to find the derivative of this function is to write square root of x squared as x squared to the power half, then use generalized power rule. So to find the derivative, put half here, x squared to the power half minus 1 times the derivative of the inside function x squared. Simplify more, cancel the 2 here, so it will be x divided by square root of x squared, which is x over absolute value of x. This is f prime, remember. All this is the derivative of the function. The derivative now is another function. If x is positive, then the absolute value will be only x. So the function becomes here 1 if x is positive, and it is minus 1 if x is negative. This is f prime, remember. So f prime at 0 is undefined because we cannot divide here by 0. So the function is not differentiable at 0. But what is happening? What do we call it here? If you try to find the limit of f prime, remember, limit of f prime from the right side or the left side, they exist. And we have seen that in example number 2, lecture number 3 in this calculus 1. So the right and left limits of the derivative, they exist, but not equal. So now that's why we call it sharp corner. We cannot draw a tangent line at the sharp corner. So no tangent line here. So it is not differentiable, and we cannot draw a tangent line, but we call it sharp corner. Why we call it sharp corner? The right and left limits of the derivative, they exist, but not equal. Let's see another example. Determine all the points where the function x, cube root of the x is not differentiable. Now we know this function is, this is the cube root of x, which is x to the power 1/3. It's continuous everywhere. Let's find the derivative. F prime is the same as dy over dx. Bring the 1/3 down, 1/3 minus 1. So now the final derivative becomes 1/3 cube root of x squared. Now if you replace here x by 0, 1/0 is undefined. So for sure the function is not differentiable at 0. But let's see. Is this a sharp corner? No. The derivative or the slope does not exist. Now let's find the limit of f prime here. See, this is f prime as x goes to 0 from the left, which is negative here. If you put negative here, you square the x, so it will be positive. Cube root of the positive is positive. So now in both cases, we have the limit of f prime is plus infinity. So right and left limits of the derivative, here f prime, do not exist, but they are equal. Plus infinity, plus infinity. Maybe minus infinity, minus infinity. They are equal. So we can say the function has vertical tangent. It's not a sharp corner. Remember, the right and left limits of the derivative do not exist, but they are equal. Plus infinity, or minus infinity, minus infinity. So we call it vertical tangent. To understand more, you will see example number 6 now. Picture will be more clear. Discuss the differentiability of this function, cube root of x squared at x equal to 0. This is not easy question, by the way. Now we know this function is continuous everywhere. This is the graph. Now let's find the derivative. Now x to the power 2/3, the derivative will be 2/3 x to the power 2/3 minus 1. 2/3 x to the power minus 1/3. Simplify more, so the derivative now becomes 2/3 cube root of x. Now if you put 0 here in the derivative, it is undefined. So f is not differentiable at 0. See, this is the third case now. The function is not differentiable at a number. This is different from sharp corner. This is different from vertical tangent. Let's check now the limit of f prime as x goes to 0 from the positive side. See, if x is positive here, the cube root is positive. So it will be plus infinity. Now the limit of the same f prime, x goes to 0 from the left here, negative side. Cube root of a negative number is negative, so it will be minus infinity. You see, the right and left limits of the derivative do not exist, and they are not equal. One is plus infinity, one is minus infinity. Or maybe this is minus infinity and this is plus infinity. So we call it a cusp. The function has a cusp. I will explain more about this strange word here, cusp. The function has a cusp at the point 0, 0. It's not a vertical tangent. It is not a sharp corner. So this is vertical cusp. In a continuous smooth curve, this is only to explain the word here. In a continuous smooth curve, if the tangent drawn line is vertical, then the function has a vertical tangent. If the vertical tangent, if you draw a vertical tangent, divides the shape of the function into two portions back to back. See, like this one here. If you draw a vertical tangent here, then you are dividing the function back to back. Then this is where we have a cusp, C-U-S-P. In mathematics, a cusp is a point on the curve where a moving point must reverse direction. Let's go back here. So if you are moving on the curve here, see at this point you start here, you have to reverse direction. Now if you go back to this one, this is a vertical tangent. If you are coming on the curve like this, you reach zero, then you continue, you don't have to reverse direction. So this is a vertical tangent, and this one is a vertical cusp. So vertical cusp, when we have the limit, remember, limit of f prime as x goes to away from the left side, plus infinity, and the other one is minus infinity. Or the limit is negative infinity, and the other one is plus infinity. Either case, it will be vertical cusp. Now I put here the four cases together where you see four cases where the derivative fails to exist. If you have a curve like this, it's continuous, but not differentiable at zero, so we call it sharp corner. We cannot draw tangent line. This is a vertical tangent. We have explained it in one example. And this is a vertical cusp. See the difference here. And this one is not continuous because there is a jump here. If we have a function like this, so this is not continuous for sure. It is not differentiable. Always check the playlist, Calculus 1 solved questions, to understand the lectures more. This is the end of lecture number 9. Thank you for watching. If you like the video, you can subscribe and share it with your friends. I hope I can see you in another video with another topic. Thank you guys for listening.